All right. Quick survey. How many of you finished MP6? MP6. Okay. Due tomorrow, right? So make sure that, really make sure that you are on track, okay? This, again, it shouldn't take too much time. If it takes a whole lot of time for you to keep up, come to my office hour. I need to find out why, right? And we have been talking about the workload for undergrad students quite a bit, and we want to make sure that we give you the the best possible way to take these classes, spend just the amount of time you need to spend in order to learn the good stuff, right? So if it takes too much time to keep up, we need to know. Otherwise, make sure that you keep up, okay? And we're going to have our second exam end of the month, and we currently have a little bit of a problem finding a room for the exam. So it may have to be shifted by a day or something. So we would let everyone know as soon as we work out all the deals and some possible deals with other classes and so on. So we'll let you guys know soon. Last week, I talked about the histogram, and also I talk about how you can, some of the nuances about formulating the convolution layer into matrix multiplication. The main insight is that because the output needs to receive contribution from multiple input feature maps or channels, the matrix multiplication, even though on surface it requires some duplication, replication of data, the fact that you use tile matrix multiplication and you have the opportunity to have each input element to be used for all the output feature, for multiple output feature map, in the tile matrix multiplication, that allows you to, to get better performance. And also, if you can begin to really think about how you're going to materialize, this is the term that we often use, to materialize that unrolled matrix. Only when you load tiles from that matrix, right? And so that you don't need to do that explicit replication process. And only when you load the matrix, tile matrix multiplication, the tiles, the input tile into the shared memory, that's where you gather all the relevant elements from the input feature maps, the original input feature maps. That's when you get the best performance. And we're going to let you work on it for a while, and we're going to come back and talk about that a couple lectures from now, and we'll keep giving you a little bit better and better information so that you can optimize better. And Carl Pearson is going to be here on Thursday, so I'm going to again try to push the material forward a little bit faster so that Carl can come and do a MV Prof demonstration. And as soon as you begin to do these performance sensitive measurements and so on, it will be helpful for you to be able to use the profiler to be able to pinpoint the benefits and the opportunities. So Carl will be here on Thursday, which should be a timely demo for you to begin to to really use and master the profiler. This also should be one of the benefits of this course. If you really take advantage of the final project, you will come out having all the necessary skills for various kinds of profilers, because MV Prof is a very, I would say, fairly sophisticated, a fairly representative profiler that you will be using when you try to tune up the performance of complex systems. Okay, so take advantage of that. So today we're going to pretty much cover the final important parallel pattern that we cover in 408. We'll cover more in 508, but this is kind of the final pattern. And then we're going to go into a few more things to solidify your understanding of the architecture and solidify your understanding of some of these concepts, such as memory coalescing and so on. with more subtleties that we would like you to have before you finish this class. So the pattern that we're going to be talking about is parallel sparse methods. So the objective for this sequence is for you to really understand the key techniques for compacting input data in parallel sparse methods for reduced consumption of memory bandwidth. So this is the sort of a very important beginning point for you to understand how people do very big data analytics, because the big data analytics invariably involve huge amount of data, and oftentimes in real world the data is sparse, and I'll go into that a little bit. So the sparse methods invariably use compaction techniques. So we use methods to be able to represent the same data with much smaller amount of the real representation, so that we can better utilize on-chip memory. When we load data into the on-chip memory, we can avoid loading any of the zero elements, and we can have fewer bytes transferred from global memory to on-chip memory. And in large-scale systems, let's say when we do these MPI-based cluster computation or Spark-based, Hadoop-based computation, oftentimes the sparse methods allow us to exchange fewer bytes of data across these nodes. And in the GPU context, another important benefit is we can better utilize the global memory. The global memory is pretty big these days, but when you start to process very large graphs, very large, sparse data, not being able to compact it, you often mean that we cannot fit the data into the global memory. And the challenge is that whenever we compress, whenever we compact these data sets, how do we retain enough of the regularity that we can still use something like a GPU that requires regularity and requires, massive parallelism, and all the threads need to do pretty much the same thing. So if we compact data, how do we maintain that regularity? How do we make sure that the memory accesses are still coalesced and so on? Okay. So we're going to take you through several steps so that you can fully understand what you're doing in MP7. MP7 is actually a fairly sophisticated sparse method. So it's a very heavily used primitive in the large-scale data analytics. So it actually takes several conceptual steps for you to really understand why and how you're doing these you're implementing these techniques so to get better and better performance. So in terms of sparse, we're going to be dealing with sparse matrix. And sparse matrix is used to model a lot of the real world phenomena. So many real world systems are sparse in nature. So for example, if you look at the US highway system, and you will see that for most of if you just open up the map, you will see that there's a few important highways going through the US, continental US. You start with highway 5, and then 10, and 5, 15, 25, and so on, all the way to 95, which is the vertical system. And then you have the horizontal system that start with 10 and go all the way up to 90. So then you will see that in each city, near each city, you're going to have a very heavy distribution of dense sub-highway systems. And near Chicago, you will see something like 290, which is a little bit offshoot of 90. And in the Bay Area, you will see 180, 280, 380, and I don't think there's a 480 yet. So all these highway systems suddenly become very, very dense, and with numerous of these offshoots to be able to bear the traffic. So if you represent the U.S. highway system, you will see a fairly interesting distribution where near major cities you have a large number of these highways, but these highways are not present in most of the continental U.S. And if you look at something like Facebook And you know what? If you look at Wenmei Hu's page, Wenmei Hu will have maybe 3 friends, and then you look at Angelina Jolie's page, you will have millions of friends, right? So you know what? So world is not fair. World is not flat. It's okay. And I'm happy with my 3 friends, and Angelina is happy with her millions of friends. But in order for Facebook to represent the entire network, they have to take into account that not everyone is connected with everyone else. There is what we call the sparse connectivity pattern, where some of the entities will have large number of connections, and some of the entities, such as me, will have a small number of connections. So whenever we model the world as a linear system, for example, we can have a connectivity model where we have all the Facebook users on one side and all these Facebook users on the other side as well. And we can put a connectivity number between in a row and column whenever the row user and the column user are friends, right? And so this essentially represents the connectivity of the Facebook world using a linear matrix, okay? And we oftentimes want to be able to use this model to solve some interesting problems and get some interesting data, and I'm going to show you a couple. So traditionally, for engineering, from many years, in the past 100 years or so, we use inverse solvers to solve many of these important engineering problems. Essentially, we was asked, if we want to get this kind of solution, what are the input, the heat or input, what are the input forces and so on that we need to use in order to create the outcome. So this is what we call the traditional inversion algorithms. And for small linear systems, we can use direct solvers such as Gaussian elimination. Many of you probably still remember the Gaussian elimination. You start from the first row. You essentially normalize the parameter, and then you do the you eliminate one of the terms, and then you go down. You go all the way down to the last row, and then you create a empty lower triangular system, and then you go back up and do this back substitution, and then you create a diagonal matrix, and at that point you have the solution for all the variables. So that's the traditional Gaussian elimination. And these Gaussian elimination processes, if we use them on the sparse matrices, we will generate a large number of what we call the fill-in elements, because we start with very few non-zero elements in the matrix. But when we try to generate that lower, so the upper triangular or the empty lower triangular system, we will end up generating a lot of non-zero elements in the upper triangular part. So that would actually blow up the the representation, and we would what we call the intermediate state of these solutions. So in the early days, when when U.S. Army tried to do something like trajectory calculation and so on, they discover a lot of these problems. When they were doing the early using the early computers to to solve these kind of problems. So it's a very old field. People have been working on these things for a long time. So the clever people, the mathematicians and so on, all understand these problems, and they say, well, if you have a very large linear matrix with very few non-zero elements, even though we all love Mr. Gauss, but the right methods would just not be practical. So people invented what we call the iterative solver algorithms. Essentially, instead of trying to inverse that matrix, what we do is we say, let's guess what the final solution is going to be. So if you look at a linear system of equations, you have the coefficient matrix, right? And then you have the all the x values, and then you have a constant vector, and then you have the y vector. So what we can do is, if we get exactly the right solution, then the coefficient matrix times all the x values in the x vector, the solution values, plus the constant vector, it should be exactly equal to the y. Okay, the y, the value given to you for the, in the original problem. So what we do is we guess. We guess what the x values should be. Okay, we take a guess, and then we use all those values in the x vector, and then we do the coefficient multiplication, coefficient vector matrix vector multiplication, and add the constant vector, and see how close we are to the y values given to us. And if the solution is perfect, then the values will match perfectly. We have the solution. But if it's not exact, there will be some errors. Okay, some errors. So we will adjust. We will adjust the x values, and using a gradient. And by the way, this should sound familiar to you, because when we talk about machine learning, that's exactly what the machine learning, the algorithms do. So we say, okay, we adjust these x values, and when we do the matrix vector multiplication again, and see if the y value is now better, right? So if we do several iterations, and if our gradient calculation is effective, then at some point the solution should be close enough. Okay, the y values that we generate should be close enough to the original y values given to us, then we declare success. So this is called iterative solver, and the most frequently used method is iterative conjugate gradient. And essentially, at every iteration, you use a method to estimate what kind of adjustment you need to make to the x, guessed x values for the next iteration, and hopefully you will converge into the right solution. So the solution of partial differential equation systems and so on can be formulated into linear operations expressed as sparse vector multiplication. So that's why in the engineering world, sparse matrix vector multiplication has been used extensively over the past several decades. Okay, so if we look at the real world, in fact, most of the real world data are sparse. Signal samples, mesh models, transportation networks, communication networks. They all have extremely sparse nature because of the distribution of cities and distribution of population and so on. So that's why it's very important to be able to master the sparse computation methods if we want to solve real world problems. And when the AI and the big data analytics started to become fashionable, the sparse methods started to gain even more importance. So here is a very simple example that my IBM friends put together for me. So this is a real world Netflix computation, where if you look at sort of the recommendation system, on one side of the matrix you have all the Netflix users. Okay, so that's the vertical direction. And then on the horizontal direction you have all the Netflix movie and show titles, right? So then you can, users, after you watch a particular title, you give Netflix a little rating and say, how good is, as far as I'm concerned, how good is this for me, right? So you will have a matrix where when the user watch a title and give a score, that score gets marked into the matrix. This is hopefully a very, very sparse system. Hopefully not all the sparse, all the Netflix users have watched all the titles. It will take a while, okay? Especially if these are my students in 408. You should be strategically watching some of the movies I recommend to you. But you shouldn't be watching all the Netflix movies, otherwise you will not be able to have time to do MPs. So this is, in reality, an extremely sparse system. And so you have all these recommendations from, sort of the evaluations from the user about these movies. So one of the important analytics that they do is the sparse matrix factorization, and that creates what we call the nominal users and the nominal titles. Okay, so this is they take a sparse matrix user item matrix and decompose that into a thin and tall matrix with all the users, and what they call the prototypical titles. And then you have all the titles, and you have the prototypical, prototypical users. So then, whenever you have a particular user that has not watched a particular movie yet, right? And so you want to generate a recommendation list for that particular user. So what they will do is they will actually say, if you look at all the movies in the past, how does this user's evaluation, how is it similar or dissimilar to other users, to the prototypical users that the first matrix indicates? So if the user belongs to one of the prototypical users, then you will look into the recommendations by those users in that in the titles, and you would hopefully see some of the titles that that this particular user has not watched yet, and then you can generate a list of those movies or titles for that particular user. So this is a very, very large computation. And then if you look at all the Netflix users, we're talking about hundreds of millions of users. And then the titles is probably hundreds of thousands of titles. So these matrices are extremely big, and they're sparse. So you don't want to represent the whole thing into mostly zeros, right? That would just take up space unnecessarily. So we would represent this as a sparse matrix, and we'll talk about that in the next few slides. So if you look at the science world and engineering world, this is a snapshot of the blue water system among all the leading science teams using the supercomputer. And this is a sort of a national, U.S. national allocation of the biggest supercomputer for the National Science Foundation, which is located only about 2 miles away from this classroom. So you will see that if you look at all across all the science applications, the number of them using sparse matrix is far more than the number of them using dense matrix. And in fact, whenever they use dense matrix, they almost always also use sparse matrix. So this is a very good indication that as we model the real world with more and more aggressive methods and then try to do better and better analysis, we will see more and more sparse computation in all the disciplines, all the way from science to engineering to entertainment and social networks. So let's focus on the perhaps arguably the most frequently used primitive sparse matrix vector multiplication, because this is the foundation for solving linear system equations using sparse methods. And so you can imagine, this is exactly what I was saying, you can imagine a linear system of 4 variables and 4 equations, right? And then, the 4 variables, x1 through x0 through x3, and then you will have the matrix, and these are the coefficient matrix. So each coefficient row defines one of the equations that you're trying to solve. So this is a constant times x0, and then another constant times x1, right? X2, so that you have the first equation is only involves variables x0 and x2. So you have 4 of these equations, and then you have the y term. So this is a typical pattern where you do you will guess a x value, and then you do the matrix vector multiplication, and you actually use a subtraction here of some kind of value, some kind of scaling of y to be able to calculate that gradient, and then you use the gradient to determine what you're going to adjust the x value in the next iteration. So this is the reason why sparse matrix vector multiplication is used so often, and there's even a name to it, SpMV. Okay, SpMV. This is a standard term in the numerical domain, and if you go into all the numerical libraries, you say SpMV, everyone knows that's sparse matrix vector multiplication. So what are the challenges for SpMV? If we compare to dense matrix multiplication, SpMV is irregular and structured and has little input data reuse. And in fact, if you look at SpMV, unlike matrix mixture multiplication, the elements in A are not reused. Okay, you take each row, you multiply that row with the x elements, and then you generate. So that's it. And then you take the next row, you multiply with the x elements. So every element in A is only used once in the matrix vector multiplication. The x elements are reused. But the x elements are reused in a very unstructured way because you have so many zeros in A that only, the x elements are only used, only a very small number of x elements is used when you do each inner product. Okay, so that's why the reuse pattern is extremely sparse and extremely irregular. So the key to maximize performance is to maximize regularity by reducing divergence and lobe imbalance. And we need to maximize DRAM burst utilization. And that's why we're going to go through several layouts, okay, several different layout arrangements before we reach the MP7, arrangement. So let's start with a very, very simple parallel sparse matrix vector multiplication. What we can do is we can say, okay, here is that little matrix, 4 by 4 matrix, and row 0 through row 3. So we can actually just assign each row to one thread, okay, to one of the threads. So thread 0 is going to be doing the row 0 inner product with the x vector, and thread 1 is going to take row 1 and do the inner product with the x vector, and so on. So this is a very natural, very simple assignment in terms of parallel computing, right? So there's nothing special about that. So, but then remember, these zeros are not represented. Okay, so we're not going to store those zeros in the sparse matrix. So what we're going to do is we're going to have compression methods. These are lossless compression methods. These methods are designed for you to be able to fully recover all the information in the sparse matrix. For those of you who watch Silicon Valley, you know what the middle out thing is a lossless compression. Remember that? You know what? And by the way, I still think it's kind of nonsense, but it's fun. It's entertaining. Okay, it's very, very entertaining. After still serving on some of the, a pretty large number of boards in these startups, some of the things are actually really funny when I watch it. So it's actually a pretty good show. So the most commonly used representation for sparse matrix is actually called CSR, compressed sparse row. And this is not necessarily only used in parallel computing. If you receive a piece of data that has a sparse matrix in that file, chances are it will come in this format, CSR, like a compressed sparse row format. And so CS does not stand for crime scene, okay? And there was one year when I had a final exam, and we asked, what is compressed CSR? And one of the answer was crime scene review. And so the student got 0.5 for creativity, but okay, points. So the CSR representation does the following. For all the, we still use row major layout. So all the elements in the row are still going to be placed consecutively in the row, in the memory. However, we'll squeeze out the zeros. Okay. So row 0 had only 2 non-zero elements, so we squeeze out those zeros. And so row 0 now is stored as only 2 elements. If you compare that to the previous one, these 2 elements came from column 0 and column 1, right? The other 2 columns are 0, so we're going to squeeze them out. So we're going to see 3 and 1 in the representation. But we have to remember the fact that they came from column 0 and column 2. So if someone looks at this piece of data and look at this and say, okay, I have 3 here and 1 here, but if I look down, I see a 0. That means that this element originally came from column 0. And this element originally came from column 2. Then I can just fill in the 0. I can just say, okay, the rest are 0. So I can fully recover the contents of that row, right? That row, and without explicitly representing the zeros. Now, when you have all these rows compressed and represented, now the rows are no longer the same length. The rows can be longer or shorter depending on the number of non-zeros in the original matrix. So we use what we call the row pointers, okay, row pointers, to tell you where each row begins in the representation. So element 0 tells you where row 0 begins. Element 1 tells you where row 1 begins. Element 2 tells you where row 2 begins. So row 0 here says, I'm going to begin in position 0, so I'm going to start with this, and then the next row starts at 2, right? The next row starts at 2, so the next row starts 0, 1, 2 here. What that means is row 0 will end in the position before it. Okay, so the row 0 will only have 0 and 1. Does that make sense? Right, so these markers tells you where each row begins. That also tells you one position before that is where the previous row ends. Right, this is a very important property. And then you could have a situation where a row is completely 0. Okay, it may happen. So if the row is completely 0, all the elements have been squeezed out, right? All the elements would have been squeezed out. So if you look at this representation, row 1 completely disappears, right? Row 1 completely disappears. However, we leave a trace. We say that row 1 starts with location 2, and also the next row also starts with location 2. When you have 2 consecutive rows starting in the same position, the first one is empty, because the one would have been ended the location before that, right? And it ended before it even started. So that's why you know that it's empty. Okay. So this way we will only represent the non-zero elements. So this is going to be the 7 elements in that previous matrix that are non-zeros. So we represented this, these 7 elements. The cost of being able to represent only the non-zero elements include the additional column index that we need to carry with each of these elements, and also these markers. So these are 1 per non-zero element, right? 1 per non-zero element, the column indices. And then the markers is 1 per original row plus 1. Okay, you need to have one more to tell you a sort of the non-existing final row begin point, so that you can use that to mark the end, essentially the end of the previous, the last row in the matrix. Okay, so you have the number of rows plus 1 in your markers. Any questions about CSR? Yes.
So for the CSR, we are showing 7 plus 7 plus 5
Yeah, yeah,
But
yeah.
even though we store the entire matrix, we're only storing about 16.
Exactly, exactly. This is a very, very good question. I was hoping that someone will ask that question. Thank you. So this is the reason why sparse matrix is only used when you have very, very small percentage of non-zeros in your original matrix. Let's say if you have a 1,000 by 1,000 matrix, okay, so that would be a million elements. But then if only 1% of your elements is non-zeros, then you only have 1,000 non-zero elements. And so 1,000 over a million, even though you have 2 times 1,000 because you need to store that index, right? And then plus all the markers, which is 1,000, so plus 1. So you will end up with 3,000 plus 1 elements, but you would be able to represent the original million elements. So it only makes sense if you have a very, very small percentage of elements in the sparse matrix, non-zero elements. Okay, and the typical distribution is that for most of the sparse matrix that we use in engineering, it's usually about 6%, or less, and then for entertainment and so on is oftentimes only 1% or less. So that's why these things are profitable. You're absolutely right. If the matrix is close to half, anywhere close to half non-zeros, then the representation will not help you or even become a negative, right? Okay. Any other questions? Very, very good. Okay. So this is CSR. It's really the stable of sparse matrix representation. Everything else is built on it. Okay, so that's why it's very, very important for you to understand how it's represented and what's the functionality of the index, the index array, and what's the functionality of the marker, right? The row pointer marker array. So we're going to call these non-zero values column indices and row pointers, the pointers to the beginning of each row. Okay, so that we're going to evolve from here. We're good? Okay. So if we look at the actual layout of the CSR, this is the picture that you should have for GPU programming. So basically we have the data and we have the column index. So these two are lined up, and then we have the row pointer on top, which tells us for every row where the beginning point of that row is in the representation. And we have one more that points to the beginning of the fictitious row. But the main functionality is to tell you that the final row really ended the position before, right? So this gives us a very convenient way to write parallel program, because when we have every thread to process one row and vector inner product, right? We can just have every thread to come to its corresponding row pointer position. Thread 0 comes here, thread 1 comes here, and then you can pick up the non-zero elements for your row. You do the matrix vector multiplication using the column index, because the column index tells you which x element you should be multiplying this element with, right? The column position of the original element picks the x element during the inner product. So you will see the use of index element, the column index, when we access the x element. And then we will use the row number to write into the y, the y output, because each row will write into one of the y elements using the row index. Okay, so this is a kernel. This is a kernel that we're going to have. All the threads will be able to find their pointers. So they're going to be finding their non-zero elements in that row, and then they will do the dot product, and they will use the column index for each element to select the right x element, and finally they will write into the corresponding y position that is exactly the row position of these threads. Okay, so and that's it. Okay, very, very simple. So now we can write a fairly simple parallel sparse matrix vector multiplication using the CSR format. We call it SpMV CSR. And as soon as we come into, so we give the kernel the number of rows. We'd say, okay, here are the total number of rows you have. And then you have the data. So these are the non-zero data elements in the array. And then the column index array, right? The column index array. And then the row pointer array, the markers, right? And then the X vector. And this is the Y vector that you're going to generate. Okay? So exactly what we said. And then we do the familiar row calculation based on the block index, block dim, and thread index, right? So that every thread will be assigned a unique row, right? A unique row to process. So now the thread comes into the if statement and say, is my row number within the number of rows, right? This is because what? The number of rows may not be the multiple of the thread blocks dimensions, right? So you say if yes, then you continue. So you do an inner product. So this is inner product. You should know inner product very well by now. You initialize the inner product as 0, and then you find the beginning position of the where you're going to find that data for your row. So this is so you go to the row pointer, right? You go to the row pointer array with that row number, right? And then you say this is the beginning index, and then the end index is row pointer of the end of the next one. So if you don't go in there, right? You need to stop one position before. So you start with row start, and you end when you continue until it's less. As long as it's less than. As soon as it's equal, then you're out, right? So this allows you to traverse all the non-zero elements in your row. And if you didn't have any non-zero element in your row, then the beginning, the element will be equal to the row end even before the first iteration, so you will go out. Okay, so you will not go into that loop at all. And then you will do so then you do the multiplication and accumulation for each of these elements. So you use the element index. The element index, you start from the start, right? Element index start from that row start. It will end one position before the next one. And then the element will be used to access data, which is exactly what you expect, right? You use the element index to access the data. But then this is something that a lot of you will have a little bit trouble with. But if you keep that picture in mind, for the data element, you also have a column index, right? So you use the element to access the column index, right? And then the column index tells you which X element should be used for the inner product. So you use that as an indirect access to X. And then you have one term of your inner product. So you do this only for the non-zero elements, because those are the only ones you will find in your data array. So the inner product is done only for the non-zero elements. So you are reducing the amount of computation you need to do to finish that inner product. All the non-zero elements are excluded from this computation. You're not wasting your time fetching zero elements, doing a 0 times something, and accumulate 0 into the final product. So this actually brings up a kind of an interesting point. Many of you who are interested in machine learning and then inference and so on, there is an active field of sparse, sparse learning and sparse neural nets, and that's exactly what this is about. So you essentially only represent the non-zero weights in elements in your system, and then you use a sparse computation, and then you will be using something like this in the inference process. Okay, so why? And then after you finish that entire the inner product for your entire row, then you write into the Y element. And the Y element, you use the row index, your row index to select the right element, and you're done. Okay? So this is a very simple, clean, pleasant-looking kernel. Okay? And this kernel even looks, as pleasant as your vector multiplication, vector addition. So here I show you the original representation, and you should see that thread 0 will come into row 0, thread 1 will have an empty row, thread 2 will come into row 2, and each of them will be going through the non-zero elements. Each of them will be using the index, column index, to fetch the vector x value, and then they all complete. Okay? So this should be a fairly simple, straightforward thing. But as simple as it is, conceptually and coding-wise, CSR kernels have two very, very bad characteristics in terms of performance. The first one is control divergence. Okay, so basically, each thread can potentially execute very different. Okay, the threads can execute very different number of iterations. It depends on the number of non-zero elements in each row. So whichever row you are assigned to, the number of non-zero elements that happen to be in that row determine the number of iterations you iterate in that for loop, right? So you may have adjacent threads that actually iterate very different number of times, because this is random. Okay, you may have a row followed by another row. One row may have, a few hundred non-zero elements. The next row next one may only have 2 elements. Who knows? So this can create tremendous amount of control divergence in each thread block, simply because you have no control over the number of iterations adjacent threads will take. Right? This data is completely determined by the data characteristics. Right? So that's one important point to make. So in this case, thread 0 has 2 iterations. Thread 1 has no iterations, and thread 2 will have 1 iteration, and that's it. Right? So you have all these wild variation of number of iterations, and that leads to control divergence in executing that for loop. And the second one is memory divergence, okay, or the uncoalesced accesses. The adjacent threads, in this case, are not accessing adjacent memory locations. Remember, every thread is going to be processing its own row, right? So the elements in the same row are consecutive, but the beginning locations of the rows are not consecutive. So when thread 0, thread 1, thread 2, thread 3 are fetching their first element in their row, they will be accessing these locations, right? That's the first iteration. And they're not accessing adjacent locations. And whenever they're not accessing adjacent locations, we have uncoalesced accesses. We're wasting the data transfer from global memory, okay? So this is the reason why the early NVIDIA libraries, that the high performance libraries that does SpMV, uses an alternative sort of a derived data structure called ELL format. And sometimes in literature, this is called ELL pack format. And this particular library was used for elliptical calculation in numerical methods, and is so popular that it has become a standard terminology. So in that particular package, they use a way to represent the sparse matrix that are more friendly to vector processing. So that, for example, the Cray computer, and then later on the Intel and IBM and so on, the vector instructions in the CPUs. And today, they are also more friendly to the GPU memory system. So here is how what we're doing. We take the CSR representation, and the CSR representation will only will only have the non-zeros for each row. But then we regularize it. This is the first time we use this term, and then you're going to hear this term a lot. The way that we regularize it is by taking these different rows of different length, and we pad them into the same length. We take the longest row, and use that as the reference, and then we pad everyone else to the length of that row by adding zeros to the end of all the other rows. So we add 1 0 here, we add 3 zeros here, and we add 1 0 here. And in the end, all the rows will be of the same length as the original longest non-zero row. Okay, the longest non-zero row. So we lost some of the benefits, right? Because now we are representing some non-zeros, right? And then we do a transpose. We transpose the matrix so that the rows becomes, the columns become rows, and the rows become columns. Right? This is a standard computation that all of you are familiar with. So when we do the transpose, we have a ELL format. The ELL format has two important characteristics. One is it's transposed from CSR. Two is all the rows have been padded to equal length. Okay, so when we have an ELL representation, we can assign each of the transposed column, which is the original row, right? Which is essentially padded original row. So we're going to assign each transposed column to these threads, and the threads will be iterating from top to bottom in their assigned columns now, right? So there are two important improvements here. One is all the threads, because of padding, all the threads are now going to execute exactly the same iterations, right? All the threads are not executing exactly the same iterations. So there's no control divergence in that for loop anymore. There's a cost, but you know we got this. The second one is all the threads are going to be accessing down the columns. So remember in C, this is what? Row major layout. So all these elements are adjacent to each other. So when all the threads access their first iteration, do the first iteration, all the threads will be accessing adjacent data elements, right, in that for loop. So you're going to have coalesce access, coalesce access, coalesce access, right? So the rest of the design is the same as the CSR kernel. So we can write a fairly simple ELL kernel. And so now if you look at the data that we send into this, you have the number of rows, you have the data array, you still have the column index, but we no longer have the pointer, the row pointer array. Why is that? Because the size has been regularized. So all the rows now, all the rows are of the same length after padding, right? So you can just calculate the beginning of the next of each row by multiplying your row number by the padded length, right? So you don't no longer need to put that into this. On the other hand, we did pay a penalty. The penalty is we're representing some zero elements. And there are situations where we'll be paying too much. Okay, so you know, if you are thinking about it, you're thinking the right way. Okay, so we'll actually get into that very, very soon. So here, we're going to, remember, we're doing this transpose access. So we're going to have a loop that goes from 0 to the number of elements in each iteration. So this is the number of elements in each padded row, right? In each padded row. And then we're going to access the data. How do we access the data? We no longer use the pointer, right? Because this is regularized. So we use the row index. Okay, we use the row index. Remember this, we're trying to access the column, right? So initially, the initial location is just the row number. The row number gives us the initial index for all the elements in that top row, right? And then whenever you iterate to the next iteration, you just multiply the current I value by the number of elements in each padded row, so that will take you to the next for each row, for each thread. So for X, it's exactly the same thing. The column index will be accessed exactly the same way. Row index plus I times the number of rows. So basically, everyone is using the row number, so 0, 1, 2, 3, and then when I is equal to 1, you add number of elements in a row to that 0, so you get to this one, right? So everyone just add the I times the number of elements in each row that take you to the appropriate location for your element down that column, right? So, and then every element will also still have that column index. So you use the column index, and access the X, and that's it, okay? So this gives you the multiplication accumulation, and in the end, you still use the row number to select one of the Y's. Even though you're doing transpose in your matrix, it doesn't affect how you write into that Y. So in the end, you still write into the Y according to your row index, and that's it. So you have a few good things about this. I already talked a little bit about it, but this gives you the intuition. Yes?
So it makes sense to me that the data rate can be populated with zeros and added location.
Yeah. Yeah. Yeah.
But what about the column?
Yeah. So that's a great question. So basically, you want to use anything that is non-trash. So the 0 is a good one. The reason is because the A value that you use will be 0. It doesn't matter which X you fetch. However, you don't want it to fetch from a bad location. So 0 is a good thing here. Yeah, right? Okay. So here, so this is kind of a little exercise that I want all of you to do, after the lecture, so that you see that during the first iteration, thread 0 through 3, for that little example, will access their initial values. So these are the initial non-zero elements that you should be fetching from the original row, right? Now it's the original. Each of their original rows now is each of their original columns, and then you move to the next one. You move to the next one, right? So so you will access 3 star 2 1 in the first iteration by all the 4 threads, and then they move to 1 star 4 1, and then star star 1 star. Okay, and when you pad here, you pad a 0, right? It's the easiest solution. Now, turns out that we actually have a little bit of issue with ELL. That is, life is not fair. Remember, life is not fair, and some of these rows may have a lot more non-zeros than others. So if you happen to have a single row that has 100 times more non-zeros than the others, then everyone else will be padded all the way to that length. So whenever you have a very non-uniform distribution of non-zeros across rows, ELL can add a huge amount of zeros into the padding. Okay, so if Facebook needs to pad all the user connections to Angelina Jolie's connections, Wenmei Hu will receive practically 100 million minus 3 zeros, okay, in my padding, right? So that's not fun, okay? So that's why you want to kind of treat Angelina Jolie specially, okay? So that's how we do it in real world. We treat these people very specially. And so we use what we call the COO format for those very special, special entities. So the COO format is a little bit, it's actually a very, very straightforward format. It's a coordinate format, and it explicitly lists both the column index and the row index for every non-zero element. Okay? So instead of using that row pointer, we just explicitly represent the row index of the elements anyway. You say, why? You know what? Why do you do that? You know what? The original CSR is very nice, right? You only need to have one pointer for every row. Now you just added even more information, you know, unnecessarily, right? So now all the rows, all the elements will now carry the column index and the row index. So the reason why COO format is useful is because when the elements can carry both their column and row index, they no longer need to be consecutive in the storage. Whenever we use that pointer, the row pointer, we assume that, you know, the row begins at that pointer and the next row begins at the next pointer, location, right? So everything in between will belong to that row. That means that all the elements of a row need to be what? Placed together. They have to stick together. And whereas if you use an explicit representation of the row index, then you can actually arbitrarily reorder the elements. The elements from different rows can be adjacent to each other. Doesn't matter. You can sort them, you can reorder them whatsoever. So here I show an example where the original representation with the sort of the conversion from CSR into a COO by adding explicit row indices into the representation. And now I can actually reorder. I can reorder all the elements as long as the column index and row index follow the data when I reorder. So for example, here 300 has been reordered here to location 5, and then 103 has been reordered to location 0. As long as the 0 and 3 follow, I can still tell that this guy really is in row 3, column 0. Okay? I can still fully recover the matrix. So this is essentially to allow us to do even more shuffling and then reordering, sorting whatsoever, as we wish, and we can still fully recover the original matrix. So here is a very simple loop that implements a sequential SpMV and COO format. So basically we just loop through all the elements, and for every element, we will take the I to index the data, and then we use the column index of I to find the X, and then we use the row index to write into the Y, and that's it, right? So we iterate through all this. So this gives us the end of the lecture, but we're going to push forward quite a bit because we need to make room for Carl Pearson's demo. Yes. Absolutely, absolutely. So very good question. So now that brings us to the next question. Very good, very good. Because you will need to use atomic operations. Yeah. Yes, for the parallel implementation. Excellent. So now, we're going to kind of continue to move forward a little bit. And hopefully we can hit JDS by the end of the lecture. So for the second part, we're going to learn to regularize irregular data with by limiting the variations with clamping, and then we're going to be sorting the data so that we can we can minimize the sort of the local variation, and we do the transposition to enable better memory coalescing. We're already seeing the ELL transposition, right? So, so we will need to learn to write a high-performance SpMV kernel based on the JDS transpose format, which is the MP7, okay? So going back to the COO format, we already talked about the COO format. Every element also carries the column index and the row index. So, reordering. I usually tell a story about the reordering, but I'm not going to tell that story anymore. I think Carl's demo is much more interesting. So in the parallel implementation, so we can think about this. So we're going to have the data and the row and column in the representation. So these are all the, each of these correspond to one element, right? And then you have a arbitrarily resorted and reordered, the collection of elements. So let's say the column, the column index of these elements tell you which X element, right? Which X element that data should be multiplied to. So I put in different colors here to show you some of these elements that, from different threads will need to, fetch the same X elements, right? So they can be very, very random. So whenever a thread process one of these data, it would need to go to the X vector and fetch the X vector. So these threads will come and fetch that red cell. And but then as soon as you do the multiplication, you take the data, you go to this X element, you do the multiplication, then you need to use the row index, right, to write into the output, right? But keep in mind that multiple of these threads can now be all wanting to write into the same Y element, because it depends on the row index, right? So all these elements are processed by different threads. So these three threads now all want to write into the Y element, the same Y element. So this is why if you have a COO format, you have a completely randomized, resorted elements, then you need to use atomic operation whenever you write into the Y element. Okay? So this is the COO format. So why is it relevant? Because the COO format gives us a tool to regularize the amount of padding, okay, to kind of control or to tune down the amount of padding we need to make when we generate the ELL format. So essentially what we do is we take the original CSR format, and then we take the rows that have excessively long, large number of non-zeros, such as Angelina Jolie, okay? So Angelina, we like you, but you don't belong here, okay? You belong in a very special place. By the way, whenever people say that you're randomly selected for a very special place, you should be nervous. So we take Angelina and move her into a very special place called COO format, okay? And then we take the rest of us, and the rest of us will have, more or less the same number of non-zeros. And we take the longest one, looks like, what's your name? Tim. Tim looks like a fairly popular, engineer. So Tim has maybe 4 elements, okay? 4 friends. I only have 3. So, so we all pat towards Tim, so we all now have 4 friends. And Angelina is sitting pretty in the COO format, and that does not, cover the world. So we take, the Tim, and then we essentially will take, we remove all these elements from Angelina Jolie. Angelina is still going to be here with 4 friends, but then the rest of her friends will be kicked out into the COO format. So in this case, we only have a padded situation where we only pad to the longest remaining, longest among all the remaining elements, and then we kick out some of these excess elements from those very, very long rows, and we put them into the COO format. So this gives us a much more controlled amount of padding. We can determine how much padding we're willing to make. So that padding allows us, then we do the transpose for the ELL. And then we use the COO format, and we write a atomic operation-based kernel to process the COO format, and then we merge the data together, and we're done. So this is called a hybrid format. So in the hybrid format, you know, if you go back to the example, we can remove one element from thread 2, from row 2. So row 2 only has 2 elements remaining in our ELL domain, and then we take that single element of that thread, thread 2, and then we move that into the COO format. So now we only need to pad 2 elements into the CSR, so we can reduce the amount of padding overhead. And now everyone has to only iterate 2 times in their for loop, and the COO kernel will take care of the rest. So this brings us to the JDS format, jagged diagonal sparse format. So this is actually probably the current GPU implementation. The libraries, all the high performance libraries now pretty much use the JDS format. And the idea is fairly simple. The idea is that you first sort all the rows into descending order according to the number of non-zeros. Okay? So if I have, let's say I have a sparse matrix with fairly widely varying number of non-zeros in each row, I do a resort, and I sort all the sort them according to the length from the most to the least, and then there will be some 0 ones here, right? When I sort them, I'm changing the order, right? I'm changing the order of these rows, but I still need to make sure that they write into the right Y element. Whatever used to be the original row 0 better write into Y0. So if I sort them, I displace them into these different locations, I better carry the information I need in the end to write into the original Y element. This is called a permutation vector. So each element will now carry what we call the permutation index. That will write, essentially is the original row index. Okay, it's the original row index that it will be used to you will use to write into a Y. And as long as we keep the row elements together when we sort them, right? As long as we're sorting entire rows, then we can just use the concept of row pointers. We can just say every row has a, we just associate the original row index for every row, right, into this vector. Okay, so you'll see a permutation vector. And using a permutation vector, we will be able to, take a row that is displaced, but then still write into the original Y element. Okay. So we first sort, and we sort them, from these kind of randomly distributed, length into this more or less, from large to small. And this is why it's called jagged diagonal, because the diagonal here is not really a diagonal, but it's kind of a zigzagging, diagonal. So this gives us a kind of a nice, smooth, somewhat smooth transition from the longest to the shortest. And the interesting part that you should be looking for when we get to the control divergence is that now the neighboring threads or the adjacent threads will be processing approximately similar, or approximately the same, or fairly similar number of non-zero elements. So there will still be control divergence, but the level of variation will be smaller. The adjacent threads will be processing very similar number. Okay, so that it will not be a very dramatic variation that cause, very large amount of control divergence. The control divergence will be somewhat minimized. So when we do the CSR to JDS conversion, and in fact, in the lab, you're going to see a function call that converts the CSR to JDS, okay, in your host code. And we actually does this conversion for you. So it's already done for you in MP7, okay? And but it's fairly simple to see. You have row 0, row 2, row 3 in the original small example. right? And then when we sort, we take the longest row, right, row 2, and make it into the new row 0, right? And then take the second longest row and the third row longest row, and then finally we'll have a 0 row after. And all the indices, all the column indices will follow, right? Will follow the elements, right, in the sort. That's fine. But then we have two things. One is we're going to need to have a new, the new values for the row indices, because after the resort, row 1 will be starting at the starting row position was be starting at 3 rather than 2, because now we have a longer row as row 0. So these values are now reflecting the beginning of these new rows, right? The new rows in the matrix. On the other hand, these numbers are the permutation indices that give you the original row number in the CSR representation. So this tells you that originally I was really row 2, and that number will be used to write into the right Y element. Okay, so this is the JDS format. So in summary, we're going to need to have a little bit more overhead for JDS compared to CSR. We still have the data, and we still have the column index, but now we still have the row pointer, even though the row pointer values need to be adjusted a little bit according to the actual length of these rows now, right? But the most important additional overhead is these indices, one index per row, that give us the original row index and that we need to use to write into Y. And so this is going to give us 2 times the number of non-zero elements, 2 times the number of original, 2 times the number of rows, and plus 1. Okay, so you will see in your study guide, there's some of these questions asking you, if you have so many zero elements in each representation, how many elements, what are the additional sizes and so on that you need to have for each different format. As long as you understand it, it's actually really, really easy to remember. Okay, but if you don't understand it, it will be a chore to try to memorize those numbers. Okay, those formula. Okay, so this brings us to this point, which is where we're going to start on Thursday. Okay, so you understand the concept of JDS. So I'm going to present the JDS kernel, and we'll go through some analysis about its divergence and this memory coalescing behavior. And then we go into JDS transposed. And then you will be ready for MP7. Okay? Good. See you on Thursday. Very good.